Okay, so to go further, I'm going to introduce something called extended Veblen notation. So we're going to go through a slight notation change from phi sub a of b to phi a comma b. And the rationale behind this is basically that we can go on and create Veblen functions with more than just two arguments. We could have like a, b, and c. So going back to gamma naught now. Gamma naught is defined as an infinite nesting of Veblen functions. And it satisfies the equation, using this notation now, that phi a of 0 is equal to a. Because we can imagine putting like an additional phi function on the top of this tower, and it's still just going to equal an infinite nesting of phi functions. So it's just going to equal gamma naught. Now what happens when we reach the limit of the two argument Veblen function is we move on to the three argument Veblen function, and we call this 1, 0, 0. And this is going to equal gamma naught. So that's just another way of writing gamma naught in extended Veblen notation. Now the fixed points of gamma naught, let's say gamma 1, the way we would construct that, exact same way as we did before, we would write phi sub gamma 1 plus 1 of 0, phi gamma naught plus 1 of 0, etc., etc. So basically we're doing the exact same thing as we did before. Basically we're escaping the fixed point trap by adding a 1. Remember, it doesn't matter how big the ordinal is. You can always add 1 and make a bigger ordinal. And then we're putting it within a fundamental sequence that would satisfy the exact same equation, phi a comma 0 is equal to a, basically. So no matter how big the ordinals get, we're always denoting the fixed points in the same kind of way, escaping the fixed point trap and then making something that satisfies the equation. How to write this in extended Veblen notation, basically, is we enumerate this last value here. So R1 would be equivalent to phi 1, 0, 1. And equivalently, if we go on, we can say, like, for instance, gamma 5 would be phi 1, 0, 5. We can have infinite ordinals in the subscript. We can have phi 1, 0, omega, so on and so forth. And eventually we reach a point where the gammas run out of power, basically. We can't go any further. We reach the point where we have an infinite nesting of gammas, and then we can't do anything else with it. And this also is the point where this satisfies the equation phi 1, 0 of a is equal to a. And what we do in this case is we enumerate the next one along. So this point is going to equal phi sub 1 sub 0. Oh, sorry. Ignore that. Phi 1, 1, 0. And that's going to be the next point. That's going to be the point of an infinite nesting of gammas. And if we want, we could call this another Greek letter. I actually don't know if this has a name or not, but let's just call it alpha naught, just for fun. We can make up whatever ordinals you want. Similarly, we could come up with alpha 1 would be phi 1, 1, 1. We continue on in this fashion. Alpha of just some arbitrary x would be phi 1, 1, x, and so on and so forth. And eventually we reach a point where the alphas run out of power, where there's an infinite nesting of them, and we can't do anything more with it. And that satisfies the equation phi 1, 1 of a is equal to a. And then we would call that phi 1, 2 of 0. And we can give that ordinal another name. Let's say beta naught. So each time we enumerate this up, whatever, we reach the limit of that ordinal, and then we have to come up with a new one, and these numbers go up. Eventually, though, we reach the point where even this runs out of power or whatever. So let's just spur of the moment, just create some kind of a new Veblen function-like type of thing or whatever to enumerate things like gamma naught, alpha, and beta. So let's say we have this here, whatever. Let's call this the gammas. We'll call this the alphas, and we'll call this the betas. And it keeps on going off in this fashion or whatever. So each time this enumerates up or whatever, you increase this value right here. Eventually, we're going to reach a point where we reach the limit of this even. And this occurs when this equation is satisfied. And this would be equivalent to having an infinite nesting of this function of functions type of thing. And when this happens, this is equivalent to phi 2, 0, 0. Now, beyond this, it gets really difficult to work with because you have to think of in your mind functions of functions and what happens when you enumerate these. Because eventually, you're going to reach a point where this runs out of power, and you end up with phi a, 0, 0 equaling a, and you have to move on to a 4-argument Veblen function. And it would be really difficult for me intuitively to think of functions of functions in which this would happen type of thing. So it gets really difficult to grasp in your mind how big these ordinals really are. And in fact, if I were to try to plug this into the fast-growing hierarchy and deconstruct it in ways we did before, I don't even think I could really do it. It gets too complicated to deal with things like this. So you could put f sub whatever, something like that. And it's going to be a huge, gigantic, disastrous number or whatever. But deconstructing it is really extremely tedious. And in order to do bigger numbers in this space, we're gonna need something a little bit more robust. We're gonna need a way of putting this into a much neater format, and that's when we get into things like infinite collapsing ordinals. So this is actually before I end this video, I'll just I'll briefly introduce something called the small, ironically called Veblen ordinal. So basically, this is a Veblen function with an infinite number of arguments, basically. So if you were to diagonalize this or whatever, we could think of this as having the fundamental sequence of I don't know where it would start, actually. Let's just say it starts at 2 or whatever. So we have like something like this. It doesn't really matter where we start, actually. So a fundamental sequence equivalent to something like this. And this is called the small Veblen ordinal. So we'll get into things like this a little bit later. But infinite collapsing ordinals is definitely the way to go to reach higher ordinals and actually being able to deconstruct them, because this format is a little bit too difficult. But it's still important to know. It's kind of neat to see how once you get into multi-arguments, these ordinals really blow up or whatever. So that's a brief overview on extended Veblen notation.